if there is a single most important topic on the lab, if I would have to single out one thing that you cannot go to the lab not knowing, that would be OSPF. OSPF is by far the most complex of all the routing protocols that you will encounter in your CCIE lab exam. It is more complex than even BGP, believe it or not. And it will be on your lab. In other news, the sky is blue. So you will have OSPF on your lab. It will be a dominant technology in both the troubleshooting and the configuration sections. In the troubleshooting section, you can expect out of 10 tickets that at least 3, 4, maybe even 5 are somehow related to OSPF. In the configuration section, in the routing protocols part, in the sections that are dealing with routing protocols, you will spend most time configuring OSPF to meet the requirements of the lab. This is why it's extremely important to understand how OSPF works, both in the single area and in multi areas. So this is exactly what I'm going to try today, is I'm going to try to explain the OSPF, how it operates, why it works the way it does, and then with a little bit of luck we're going to see it in action. So when it comes to OSPF, it's important to understand that fundamentally speaking, it is a link state routing protocol. Now, this is what the books say. Now, which you probably have already noticed, don't always agree with books. So yes, OSPF is link state in a way, but I prefer to think of OSPF as hybrid routing protocol. Now, why hybrid? Because inside a single area, OSPF is indeed a link state. But when we go into multi-area operations, as you will see, OSPF actually behaves in a very, very distance vector way. So hence, the hybrid thing. Now, if you read RFC for OSPF, and RFC is 2328, if my memory serves me well, you are of course not going to see the mention of the word hybrid. You are not going to see the mention of distance vector behavior, but you are going to read about something that is called partial SPF. And when you actually read and understand what that is, you're going to realize that they are actually describing a distance vector behavior of the routing protocol. Now, that said, for the purposes of the written test, if you are studying for your written test, just remember OSPF is a link state routing protocol. But from practical perspective, from a practical point of view, it is actually hybrid. Now, for the sake of argument, I will just say that this is also true for ISIS. ISIS is also, in a way, a hybrid routing protocol, but you don't care about the ISIS, so I'm not going to waste too much time actually talking about these two. So when we talk about OSPF, it's very important to understand that, explaining OSPF for an instructor that is trying to teach you at the level that you need for CCIE, we are presented with multiple challenges. First, I can either make an assumption that you know how OSPF works and that I just need to show you some advanced configurations. But as I said, at this point in my life, I have done a few CCIE bootcamps and I have seen so many misconceptions about the OSPF, and being that I consider it to be a single most important topic for the exam, I'm going to try to avoid making too many assumptions about what you know. So I'm going to try to explain OSPF from ground up. But as I said, sometimes we as the instructors are faced with an incredible challenge there, is that sometimes we have to explain some behavior using the terminology or using related behavior in OSPF that we have not yet explained. So we are going to be playing chicken and the egg situation pretty much all the time. So I can start talking about OSPF from ground up, but then I'm going to talk about the information exchange. But how do I talk about the information exchange before I explain what is contained in those information exchanges? But if I talk about that, then how do they propagate? And then we're going to talk about the areas, but what are the areas and what are the different area types? So you see, it can get very, very complex real fast. So I need to make a decision here. So what I'm going to be doing here is I'm going to be explaining things in OSPF relatively from ground up. And then I'm going to go on tangents explaining OSPF. So I'm going to talk about one thing. So we are going to be, as you will see, filling up some tables. And then as we fill out those tables, I'm going to go on tangents and explain relative concepts that are related to what I was just talking about. And that means that we are going to be jumping a little bit back and forth in this lecture, but I hope that you will be able to follow me. The OSPF network types table. The first network type that I'm going to talk about is going to be the broadcast network type. Now, broadcast network type is using hello timers, or it sends hellos every 10 seconds, and it uses the dead timer of 40 seconds. Now, this 10-40, or I should say 1-to-4 ratio between hello timers and dead timers, is the default one in OSPF. So if you change just the hello type on an interface, for example, the hello timer on the interface, you're automatically going to be modifying the dead timer as well. So if I set my hello timer to 20 seconds, my dead interval will automatically be 80 seconds, and so on. So this ratio is maintained until the moment you actually set the dead interval manually. The minimum that you can set for the hello timer in OSPF is 1 second. But sometimes you actually want to have a fast convergence, that you want the routers to notice that the neighbor is down in shorter time than 1 second. If that is the case, you have to use the special configuration in which you declare that you want to use the minimal dead interval, and the minimum dead interval that you can set is 1 second. And then you configure something that is called the hello multiplier. Within that 1 second, how many hellos you want to send. So if you say something like IPOSPF dead interval minimal, and then hello multiplier 4, you will be sending hellos every 250 milliseconds on that interface. Now, this is something that can be used to provide for a sub-second convergence on that interface, and is also something that can very reliably provide for a complete meltdown in your network. So be very, very careful when you use these features, and I can tell you from my personal experience that they sound much better than they actually are, and I am not joking about the meltdown part. Now, in the hello column here, I'm going to mention that on the broadcast network type, by default, it will be the multicast hellos that are being sent. And OSPF sends hellos to 224.0.0.5. So the hello destination, so let me just write this down. So we have hello destination for multicast is 224.0.0.5. Now, this is a link local address, which means that traffic sent to this address will not be routed by other routers. So these hellos will be contained to a specific interface, to a specific link. Neighbor column here, do I need to specify the neighbor statement in order to establish successful adjacency on a broadcast network type? The answer is no. I don't need the neighbor statements. I don't need to specify the neighbors. And this goes hand in hand with the fact that we are using the multicast hellos, because if we are using multicast hellos, we don't need to have the neighbor statement, because that's the whole idea of using the multicast hellos, is that we don't need to know what the neighbor is, and it will be simply delivered to all OSPF routers. The hello message will be delivered to all OSPF routers. Is there DR, BDR election? The answer is yes. And here I'm going to go on a first longer tangent, and I'm going to talk about what the DR is, or the designated router. Designated router on a shared segment. So let's say that we have a segment of routers that are connected to the same Ethernet link. So something along these lines. So here, let's say that we have routers 1, 2, 3, 4, and 5. Now, I represented Ethernet as just a bus, but this is, of course, in these days all connected to the switch. But the idea is the same. If one router here sends a packet, sends a multicast packet, it will actually be delivered to all of these routers here. Now, one of the requirements of OSPF is that the database that OSPF uses to keep information about the network, to calculate the best path, and I will talk about the database a little bit later on in greater detail. One of the requirements is that inside an area, a database must be identical on all devices. So whatever is on one of these routers must be present on all the other routers. Now, keep in mind here that when I say area, I don't necessarily mean just this one segment. We could have other routers, for example, connected on point-to-point links or another shared segments here that are in the same area. And this database requirement that it needs to be identical holds true for all those routers as well. So all these routers here must actually have identical databases because they are in the same OSPF area. So this is an area, and this part here, this arrangement between 1, 2, 3, 4, and 5, this is something that we are going to call a shared segment. Now, inside an area, we can have multiple shared segments. Here is another one. So this is another, let me use a different color there. So this here is going to be another shared segment that is very, very different than the one on top. So they are unrelated in terms of DR election or the BDR election. These are separate shared segments. So we have one shared segment here and we have another shared segment here, but they are in the same area and they need to have identical databases. So going back to our shared network, just focusing on that one bit. So we are going to have 4 routers here. If the database must be identical on all of them, let's examine what happens. So I'm just going to copy all this. What happens if, for example, R1 here has a network N that it is advertising to all these routers? So what it's going to do is going to send the network here, going to send the advertisements here, send the advertisement here, and send the advertisement here. Now we can see that we are sending this advertisement here 4 times. But not only that, we need to maintain the adjacency with R5, we need to maintain the adjacency with R2, we need to maintain adjacency with R3, and we need to maintain adjacency with R4. R2 needs to maintain adjacency with R1, with R5, with R3, and R4. R3 needs to maintain adjacency with R5 and R4 on top of that, and R4 and R5 have the adjacency. So basically what I have here is the full mesh of adjacencies, which on 5 routers isn't really that much of a deal because every single router here will have only 4 adjacencies. But what if we had 50, 60 routers on this segment? Now, not very likely scenario, but also not extremely unlikely scenario. This number here doesn't really scale well. And especially given the fact that information that is sent by R1 to R2 is the identical information that is sent to R5, R3, and R4, and in the other direction. So we are simply going to be sending the exact same copy of the same information to all of the routers on the segment. Now, this is not very scalable and it's not most optimum way of actually exchanging the information. This is why in OSPF there is this concept of the designated router, which basically is the router that is going to be acting as a virtual hub for the exchange of the information. So not all traffic will be flowing through it as the result. It's just going to be an exchange hub. So in this case, let's just say that for whatever reason, R5 here became our designated router. What's going to happen is that R5 is going to maintain the adjacencies with these 4 routers here. So the number of adjacencies is now n-1 in our network. That means that we have this virtual hub and spoke of information exchange. So when we have our network N here from R1 that needs to get advertised, what's going to happen is R1 is going to send that information to R5, and R5 will fan it out where it needs to go. So we are not going to send the same information from R1 to R5, from R1 to R2, from R1 to R3, from R1 to R4, and then from R5 to 2, 3, 4, then from 2 send it to 3 and 4, then from 3 send it to 4, and then from 4 send it to 5. So this is not going to happen. This ridiculous exchange of information of the exact same information. So this is the primary role of the designated router, is to provide this hub and spoke like information exchange inside the shared segment. That's the primary role of it. Another role of DR, and this is going to get a little bit tricky now. Let's say that we have an area that involves a lot of shared segments, or maybe even some point-to-point links. That really doesn't matter. So some relatively complex network. So this is a single area. Inside this area, as we can see, we have multiple shared segments. So we have this shared segment, we have this one, we have this one, and we have this one here. So on each and every one of these shared segments, one of the routers is going to be the DR. So I have circled them here. As you can see, these DRs are not connected to the rest of the network. These routers are not connecting elsewhere. So these routers here are providing for a virtual hub and spoke communication inside these shared segments on which they are in charge of. So this is their primary role. So this is the primary role. They provide for that hub and spoke. But there is also a secondary role. Now, the secondary role is to inform all other routers in the area about the arrangement that may exist on this segment here. Now, what these routers here are going to do, let's say this DR here, let's call it DR1. What it's going to do, it's going to generate information. I'm going to talk about this. Technically, it is type 2 LSA, but I will talk about LSA types later on. It's going to generate type 2 LSA, informing other routers in the network that there is this shared segment here that consists of, let's say, routers 1, 2, and 3. So it's going to generate this information and send it to its neighbors. So it's going to send it to R2, it's going to send it to R3. Now R3, due to the nature of the requirement that the database must be identical in the whole area, is going to actually flood this information to other routers. So this information that shared segment exists is going to flow through the network. So all these routers here are going to become fully aware that this arrangement here exists. This DR here is going to do the same thing for this shared segment. This DR will do that for this shared segment, and this DR will do that for this shared segment. So there are these two roles of the designated router. Now, this role here that I call the primary role is much, much more important than the secondary one. And for that purpose, on this shared segment, not only that we are going to have the designated router, we are, in most cases, going to have a backup designated router. So these are the adjacencies with the designated router. And let's say that one of these routers, let's say that R3 here, was elected to be the backup designated router. The BDR will maintain the adjacency with the DR, so this adjacency here exists, but it's also going to maintain adjacencies with all other routers. So the actual number of adjacencies is going to be 2 times n minus 1 in our network, which is still much, much fewer adjacencies than we have with full mesh. Now, the reason here is that if this router here was to unexpectedly die, we are still going to have the information exchange available through our backup designated router. Now, what BDR is not going to do is this stuff here. the secondary role. There is no secondary role for the BDR. So I'm just going to write this down. So DR is the only router who is responsible for informing the others using type 2 LSA about the arrangement on the segment. Now, if DR was to unexpectedly disappear from the network, the BDR will actually get promoted to the DR, and then it will be sending this information. And one of the other routers may actually get promoted to become the BDR. Now, when the BDR gets promoted to the DR, it will send this type 2 LSA, and the rest of the network will know that arrangement still exists. There is, in most cases, no actual loss of traffic, because if we take a look at this arrangement here, let's say that this router here was the DR, and this router disappeared from the network. Now, let's say that this router was the backup designated router. Was this designated router actually connected to the rest of the network? The answer is no. So these other routers still know, technically speaking, how to reach to this network through this router R3. The fact that for a brief period of time they had stale information from the DR doesn't matter, because now they're going to get updated information from R2 that is going to be almost identical. The only thing that is going to be missing there is R1. Why? Because R1 disappeared from the network. So now we are getting updated information that R1 is no longer connected to that shared segment, which is actually true. But for a very, very brief period of time, these other routers in the network were under the impression that this network functioned properly, but they could still reach 2 and 3. Yes, we were blackholing traffic to R1, but that's fact of life. Why did it disappear from the network? But when we receive the updated information, these routers are no longer going to think that R1 is reachable through that network. So that is the role of the DR, and that is the role of the BDR. Now, how are DR and BDR chosen on the network? So I'm going to go through DR and BDR election process. Now, I'm going to say election under quotes here because it is actually a dictatorship. And having lived under one, I can tell you that the only good way to get rid of the dictators is to shoot them. But that's me digressing. Now, let's say that we have several routers that are actually connected to the network, and we need to elect the designated router. Now, in OSPF, all routers are identified to other routers using something that is called the router ID. Now, quick digression here, router ID is a 32-bit number that looks like an IP address, but is not an IP address. What I mean by that is that when you have router R1, and this R1 has multiple interfaces, let's say that it has Ethernet interface, it has serial interface, it has gigabit interface, and it has the loopback interface. All of these interfaces will have an IP address. Now, when we fire up the router OSPF process, what's going to happen? An IP address from one of these interfaces is going to be used to become a router ID. If you have a loopback interface, this IP address will be used to become the router ID. But it is going to be the value of the IP address that is used, because router ID is not an IP address. So let's say that we had 1111 here. So the router ID here will become 1111. Now, let's say that we actually remove this interface from the router. Our router ID stays 1111, and everything functions normally because router ID does not have to be a reachable IP address. It's just a 32-bit number that looks and feels like an IP address, but is not actually an IP address. Now, why am I saying this? Is that you can have a perfectly legitimate scenario. Good luck troubleshooting this, but this is a perfectly legitimate scenario where you have, for example, R1 and R2, and let's say that both of them have loopback 0 interfaces, and this is 1, 1, 1, 1, and this is 2, 2, 2, 2, and the router ID on R1 is 2, 2, 2, 2, and router ID on 2 is 1, 1, 1, 1. This is a perfectly okay scenario. OSPF will work perfectly, sorry about this. So OSPF will work like a charm here. It's only you who will struggle to actually troubleshoot this in case there is a problem, because you will see that there is a loopback that has IP address and then you have a router ID that doesn't match. Now, the reason why most candidates or most network engineers would struggle with this is that our immediate gut feeling is, oh, router ID is an actual IP address. Just remember this, it looks like an IP address, but it's not an IP address. Another example is, for example, this. This is a perfectly valid router ID. Now, this is very invalid IP address, but this is an okay router ID. So, inside our OSPF, each router here has a router ID. A router cannot operate in OSPF network unless it has a router ID assigned. By default, it will be assigned from one of the interface IP addresses. Loopbacks are given preference. If there are no loopbacks configured, then it will be simply the highest IP address on the router. They can also be configured manually under the OSPF process with router OSPF, whatever the process number is, and then you specify the router ID. And let's say that here router IDs are very, very simple. Now, when these routers become active on this segment, the router IDs are going to be one of two things that are going to be used to determine which one of these becomes the designated router. The second thing is going to be priority, or the router priority. This is a per interface setting. So on different interfaces on the router, we can have different OSPF priorities. The default priority on OSPF routers, on Cisco routers is 1. So we can see here that all of our 3 routers have priority of 1. Priority is the first thing that is taken into account. So priority, and then the router ID. And the higher value is the one that is given preference to. So in our case here, what's going to happen is that R3 is going to become the designated router. Why? Because the priority is the same on all 3 of them, and then it will be the higher router ID that becomes the DR. Our R2 here will become the backup designated router. Now, this is all nice and fine, except for one thing. If R1 booted first, R1 would be the only router on the network. It would ask, are there any DRs on the network? If there are no DRs on the network, R1 would actually be promoted DR. So, going to write this again here, DR election. Important thing is, there is no preemption. New router will not displace existing DR. So if DR already exists on the segment, it will not be replaced by any new router, no matter how better the preference is on that router, or how better priority is on that router, or how higher the router ID is, which creates a unique set of problems. Because when you have a network, for example, that is hub and spoke. So here we have a hub and spoke network. And what I mean by hub and spoke is that this here is a single interface. So I'm not talking about the sub interfaces, I'm talking about single individual interfaces. So this is a hub and this is a spoke 1, this is spoke 2. Now, when you have a scenario that looks like this, it's very, very important that the hub here is the DR. Why? Let's take a look at the hellos. If the hello here is sent, and it's sent to 224005, and remember that I mentioned it's very, very significant to remember that this is a link local address. This will be received by the hub, but it will not actually be forwarded out. The same thing happens with the hello from spoke 2. This router will be aware of this spoke, but it will not send these hellos. Now, of course, hub itself is going to send hellos, so we might actually have a valid adjacency here, and we might have a valid adjacency here. Now, let's say that the router ID here was 3333, that here was 2222, and that here we had 1111. What's going to happen here is that, and this is from hub's perspective, is that hub is going to think that on this segment, this is the DR, and that spoke 2 is the BDR. And it's going to think that it's DR other. Now, what's going to happen here is, let's say that there is a network N behind spoke 1. And let's say that this network N is now being advertised to hub. Now, the hub, being DR other, assumes that there is an adjacency between spoke 1 and spoke 2, so it's not actually going to reflood this LSA to spoke 2, which means that spoke 2 cannot reach the network N. So network N is unreachable from spoke 2 because hub did not forward that information out to it. This is why whenever you have hub and spoke networks, you need to absolutely ensure that if you are using the network type that elects the DR and the BDR, you actually need to make sure that the hub is the DR. And you need to ensure that no other routers in that segment can ever become the designated routers. Which brings me to another point. The only way, so again, DR election. The only way to prevent, the only way to make sure a certain device is the DR is to ensure no one else is eligible. Why? Because of the preemption. So I'm going to repeat that, no preemption. How do we make sure that routers are not eligible to become DRs? Not eligible are the routers that have priority of 0. So in a case of our hub and spoke environment, here, what we really need to do is we need to set the priority here to 0, and we need to set priority here to 0, and we need to set priority here to a non-zero value. Personal preference for me is to set it to 255, just to be absolutely sure it will be the DR, even though it makes no sense. 1 is enough. So this is the crucial part. Whenever you are dealing with hub and spoke environments, on your spokes, you need to make sure that your spokes have the priority set to 0. If you don't set the priority to 0, you are going to have a problem. Now, hub and spoke environment is relatively easy to spot. Of course, it's going to be frame relay, but also private VLANs. Now, imagine what private VLANs are doing. So let's say here that we have, again, 3 routers. They are connected to an Ethernet segment. Now, on an Ethernet segment, we know that everyone here, so let's say R1, R2, and R3, that everyone here can communicate with everyone, right? This is the same broadcast domain, so they can communicate with each other. But when we add the private VLANs, basically what we are going to be doing, let's say that this one here is the promiscuous port and that these are in isolated VLAN. What we are creating really is this. We are creating two broadcast domains. We have one broadcast domain here and we have another broadcast domain here. So these guys can freely communicate. So there is a free communication here and there is a free communication here. But this device cannot communicate to this one. So R1 and R3 cannot communicate. Their only way of communicating is through R2, which basically makes R2 be the hub and these are spokes. So this is spoke and this is spoke, which means that we actually have a hub and spoke setup on Ethernet, which is very, very unnatural thing for Ethernet because everyone is supposed to be able to communicate with everyone, but they cannot communicate with each other because the private VLAN configuration is preventing this from communicating. So this is the long story about the DR election, and the situations in which you need to actually take care of it. So going back to our table, here just a reminder, on a broadcast network type, if you remember that we are actually filling out some table, on a broadcast network type we do have DR and BDR election. Now the next field in this table is mask. Now, what do I mean by mask? This is what I mean by mask. Whenever we have a router configured, and let's say that it has an interface, and this is an Ethernet interface, so it's Ethernet 0.0, and let's say that we have an IP address 192.168.151.17, and it's configured as /24, for example. When we want to advertise this network here, in OSPF. And this is the default, so this is the broadcast network type. Which mask is it going to be advertised? Is it going to be this mask or is it going to be something else that gets advertised? Now, let's say that this was /27, for example, or let's say that it was /28 or 29, it doesn't matter what it was. When you are dealing with the broadcast network type, it will be the correct mask that gets advertised. So whatever is actually configured on the interface will be that ends up being advertised in OSPF. Now this might look pointless and straightforward, that, I mean, what else could it possibly be? But bear with me, there is a reason why I'm explaining this. Now, next hop, this is a really important one. Imagine a network scenario that looks like this. So we have 3 routers and they are connected to the shared segment. And let's say that this router here is the designated router and these two are DR other. So I don't care about the BDR at this moment. So this is R1, this is R2, and this is R3. And there is some network N behind R1. Now, when network N is advertised in OSPF, we know that R1 will actually advertise it to R2, and R2 will somehow advertise this network to R3. So R3 is now going to have a network, but what is going to be the next hop for this route? What is going to be the next hop? Is it going to be R2 or is it going to be R1? Now, in a broadcast network type, the fact that R2 actually re-advertised this route is irrelevant. The next hop will still be the interface of the router R1 in this shared segment. So basically, it will be R1, or as I like to say, it will be unchanged because the hub side here, the DR, is not going to change the next hop when it re-advertises the route. Very straightforward and no problems with this. Except Actually, let me give you a more relevant example. So, in an Ethernet setup like this, with R1, R2, and R3, this is not a big deal. But what if we actually had a private VLAN here? So what if this was isolated? This was isolated, and this was a promiscuous port. So we have taken care of the fact that R2 is the DR. That's good. But what happens with the actual traffic? When this route gets advertised to R2, and R2 sends this information to R3, and R3 knows that network N is reachable through R1, when it wants to send the traffic out, it's actually going to send out the ARP request. And who has, and let's just use this as, who has R1's address? I'm looking for the next hop for the route. I know that network N is reachable through this address, but I don't have the MAC address for it. When R2 receives this ARP request, which is broadcast, remember, this is one broadcast domain, and this is another broadcast domain. They are separated. R2 is going to receive this broadcast, this ARP request, and is going to say, well, that's not me. Then R3 is going to resend it. Hey, who has R1? And R2 is going to think to itself, well, this is not for me. This is for someone else. So basically, R3 cannot communicate with network N because it cannot go through the hub, because the next hop here was unchanged. Now, in order to fix this, if this was a broadcast network type, again, I'm repeating, we are dealing with the broadcast network type behavior in OSPF. In order to fix this, we need to implement a special hack on this interface here. What we need to do is configure IP local proxy ARP. Now, what IP local proxy ARP is going to do is when this ARP request here arrives to R2, R2 is going to respond back and say, okay, you know what? I have this IP address. So now R3 can actually send traffic to R2, and R2 can route it to R1 because R2 knows how to reach R1. So basically, we are forcing the traffic to go through the hub. We are working around the limitations of Ethernet. But remember, it's the IP local proxy ARP, not to be confused with the proxy ARP. Proxy ARP, if enabled on R2, would respond to ARP requests for anything except for the local segment. So all the questions that are dealing with the local segment, R2 will not answer if only proxy ARP was configured. But if R2 had some other network, it would answer with its own IP address and saying, yeah, with its own MAC address and saying, yes, this is me. But when we configure the local proxy ARP, R2 will actually respond to this ARP request even for other addresses that might appear to be on the same network. And this is the scenario in which you might end up using this. So going back here, the next hop is unchanged. Now, and here the default column deals with, is this network type a default on any interfaces in OSPF? Yes, it is default on all Ethernet interfaces on all types of Ethernet interfaces. So if we have fast Ethernet, gigabit Ethernet, 10 gig, 40 gig Ethernet, 100 gig Ethernet, whatever it is, the broadcast network type will be the default network type. The question I had here is, will clearing of the routing process in all the routers take care of preemption? So if we already have a DR configured on the network, and if we clear the router process on all the routers on the segment, will they go through re-election process? The answer is yes. But again, make sure to do it relatively close to each other, because if you wait too long between them, one of them may declare itself as the DR. The routers have a built-in defense mechanism against this, and I will talk about it in a moment. But Yes, the short answer is yes. You can do it, but don't wait too long between clearing processes. But if you do it within a couple of seconds of each other, actually you do have a little bit more than just a couple of seconds, you will be fine. So that can take care of preemption process. But really, the only thing that you have to do is just clear the process on the elected DR. You don't have to clear it on all of them. Because if you clear the DR and it's no longer sending the hellos, after the dead interval expires, after 40 seconds, all other routers are actually going to declare the DR as dead, and they're going to go through the re-election. So the one that was BDR will be promoted, and a new BDR will be elected. If you want to change both DR and the BDR, just clear the process on two of them, and the DR others will actually go through the election process, if, of course, they are eligible to become DR and the BDR. That means that they must have their priorities as non-zero.